Hi everybody, this is Dr. Bricker here with a video for our next lab, which is electric and potential fields. So when you log into Pivot, you'll see something similar to this, but not the same because I've got different classes than you. So we're doing electric and potential fields PNW. And let me view it. So this one is 50 points, and there's several different sections as you go through here. Experiment 1 through 5, and I just kind of want to let you see what it looks like and talk a little bit about the notation here. So this is going to be it's called a PHET lab, Physics Education Technology. So if you click here, charges and fields, this is going to open up another tab, and this is what the lab is based on. So you see some charges here. This is all spelled out in the lab, by the way. +1 nanocoulomb, -1 nanocoulomb, some sensors, different things you can pick here. This is a voltmeter, this is a ruler here. This button is to reset the whole thing. This button down here does a few things. You can take a screenshot with this, which you'll have to upload a couple of pictures, so that's a nice way of doing it. You can also go to full screen so you can see it a little bit better. If you click options here, you can do projector mode, if maybe that looks better to you. I just prefer it to be like this. Projector mode's fine too, though. So play around with that. I can put a grid here, then I can take a charge and put it wherever I want to. So I can just put it here, and you can see the direction of the electric field then. You can put some values on here. So I can take a sensor, move it around, and you can see 9.28 volts per meter. That's the electric field strength at 0 degrees. It's easier to see if you go to full screen mode, kind of like that. To get out of full screen mode, just hit the escape button. Okay, and you can move the sensor around. Here's the length here. This is 1 meter, so I'm 1 meter away. The electric field is 9.28 volts per meter at 0 degrees. Okay, and you can kind of get an idea when you move the sensor around. I'm moving the sensor here. I'm about twice as far away, and you can see it's -0.4 degrees, so I can actually move it up a little bit if I wanted to be right on the horizontal axis. 2.28 volts per meter. Okay, here's the voltage button I can hit, and then I can read different voltages. So this is the electric field strength. You can tell by the units here. Here's the voltage at this spot, pretty close to 4.532. And if I want to look at an equipotential surface where the voltage is all the same, I can hit this button. So anywhere on this surface, then we've got 4.32, or I can get rid of it then. Okay, so pretty cool. You can take another charge, put it up here, add more charges if you want to. This is actually a dipole then, positive charge, negative charge. If I want to, I can take the meter, move it back here. If I don't want to see the value, I can click, unselect this. Right now I'm at 179.4 degrees, so if I wanted it to really be down here at -180, I'd have to move the sensor down a little bit. So you have to play around with it. Okay, almost there. Something like that. Okay. Anyway, this is basically how it works. You can take more charges and add more charges if you wanted to. And then the electric field you see is because of all of the charges. And if you want to remove it, you just take it and move it back here. If I don't want this one, I can move it back here. Okay, so this first part I just wanted to kind of show you how it worked. You can play around with it and get an idea of how it works just by playing around with it in the beginning. Okay, let's go back to the actual lab. Hit escape, and then go back here. So this first part just talks about how that thing works. So, read through it. But this is called your workspace here. And then we've got the first actual experiment. So go through and answer these questions. Positive charge, you're familiar with what the electric field looks like for a positive charge. Answer these questions. Okay, I don't want to give too much away. And then you can move the charges into different positions, that sort of thing. good. A little data table to fill out, and then you'll be able to tell how the electric field strength depends on the distance from the charges and what it looks like if it's a positive charge or a negative charge. Okay, very good. Electric field of multiple charges. This is where we're going to look at a dipole actually. So we'll have one charge here and one charge here, and it tells you where to put each. So in this one, a dipole, that's what a dipole is, a positive and negative charge separated. So you'll create an electric dipole, pair of charges, equal magnitude, opposite charge. Place one positive charge and one negative charge 2 meters apart on the horizontal axis with a positive charge on the left. So positive charge over here, negative charge over here. And then you want to know what happens to the electric field as you go in this region. What happens to the electric field? What happens in the electric field between the charges? This is the second region. This is the third region, fourth region above here, fifth region here. Okay, so we're not really interested in the values. We're just looking at, as it says here, turn off the values, describe the field by dragging the sensor along here and etc. along the other ones. So this part's worth 5 points. 1, 2, 3, 4, 5. What happens in the first region, second, third, fourth, fifth? Okay, and is there any place where you can find 0? Similar thing here. Remove the negative charge, replace it with the positive. So now you've got 2 positive charges. Do the same thing. Go through the 5 regions. Talk about what happens. And is there a place where it's 0? Okay, electrical potential, or in other words voltage, that's the third experiment here, so we'll actually be using the meter here. Okay, so reset the animation, turn off the electric field option, place one positive charge in the center of the grid on the intersection of major grid lines. Probably you want to go to full screen mode to make it a little easier to see. Take the voltmeter, move it around the grid, and then move the voltmeter in a circle around the charge. Describe how the electrical potential changes as you move closer to the charge. Okay, and we've got the formula in the book for what the potential of a point charge looks like. That's from chapter 21. Okay, I don't want to give too much away there. Same idea, remove the positive charge, replace it with the negative charge, and then repeat what you've done there. Okay, and then kind of just go through here. It spells out everything. I don't want to read all of these for you, but this will tell you where to put charges. Create an electric dipole as you did in step 2 of experiment 2, and then go ahead and fill out the data table. There's a little bit over here too. So potential, that means voltage again. Okay. Experiment 4, relationship between electric field and electric potential. Okay. It's pretty well laid out here. There's a lot of words to read, but just go through it. Usually the lab, we're in there for 2 hours, as you know, if we were meeting in person, and then you work on the lab before. So expect to spend a couple hours at least working on this. Okay, so place 2 positive charges and 2 negative charges at 4 random points on the workspace. So we're really getting more here. Turn off the electric field and turn on the values option. Place the voltmeter anywhere in the vicinity of the charges and click the pencil icon. Remember, the pencil icon will do equipotential surfaces. So this, as it says here, green equipotential lines. So you'll be able to see different equipotential surfaces for asymmetric distributions of charges. So you don't, random spots don't make it nice and uniform. Okay. And then go through and answer the questions here. Okay, I don't want to give too much away. From what we've done before in class, though, here's a little hint. The equipotential surfaces, this is from chapter 21, the electric field always crosses equipotential surfaces at a right angle. Because think of it like this, the equipotential surfaces are like the same elevation on a topographical map. So no part of the gravitational field points along the same direction that you're walking, right? Gravity is pointing straight down. It's not pointing along the path you're taking if you're walking around the same height. It's the same thing with voltage. If you're on an equipotential surface, no part of the electric field points along the equipotential surface. If it did, you would be accelerating as you went around the surface, and you're not. You're at the same voltage. Okay. So you'll see that in this part. Finally, the last part, the notation is slightly different, but it's the same formula. Now in class we have electric field is minus delta V over the distance. Here they're using delta phi. So when you see this symbol phi, this is phi. We used V for it. Here it's just using phi. Okay, so be careful with that. We did some homework questions on that actually. Calculating the electric field from different equipotential, between different equipotential lines. Okay, so this is a reminder how this is actually measured. So here we're going to be able to figure out the X part of the electric field and the Y part of the electric field, and then from that get the overall electric field. So this is probably the hardest part. So we'll do something like this arrangement here. So you can figure out again the voltage difference from like B to A, and then the distance from B to A, and then get the electric field in the X direction from that. The voltage difference in this direction, voltage at C and D, and the distance between those points, and get the electric field in that direction. And then once you know the electric field in the X direction and also the electric field in the Y direction, you can get the net electric field. It's the X part squared plus the Y part squared, the square root of that. Okay, and that's all spelled out here. This is what I've just said. You know, get the electric field in the X direction from using the voltage difference, A minus B, and then same thing with the Y direction. You know, the C and D part was up and down. And then the magnitude is the X part squared plus the Y part squared, the square root of that whole thing. And then once you have the X and Y part, you can figure out the angle, right? You have to think of what the tangent represents. I don't want to give too much away. You know, tangent of theta, rise over run, that sort of thing. Okay, and then you can check it. You can actually measure the electric field at that point and see how the number that you calculated corresponds to that. Now you should get a pretty good answer here. Okay, send any questions and I will talk to you soon. Bye-bye.